Okay, welcome everyone to this new talk on for the DEGA webinar series. So it's my pleasure to welcome Alejandro Ribeiro. He received his bachelor degree in so he got his bachelor degree in Uruguay in 98. And then he got his master's and PhD from the Department of Electrical and Computer Engineering at the University of Minnesota. That was back in 2007. And then he joined the University of Pennsylvania in 2008, where he's now a full professor doing research on autonomous networks, wireless networks, machine learning on network data, and distributed collaborative learning. He received several paper awards, for instance, the 2014 Hugo Schuck Best Paper Award, and then also several Best Conference Paper Awards, for instance, at USIPCO, at ICASP, CDC, the SSP Workshop, the SUN Workshop, ACC Conference, and also Silomar. So a lot of nice contributions and paper awards. Alejandro is also being recognized for his excellent teaching qualities. He received two nice teaching awards for that. So we have a highly decorated speaker today, so looking forward to his presentation. So go ahead, Alejandro.
Okay. Well, so thanks a lot, Geir, for the introduction. Thanks a lot to To, Geert, and Dorina for the invitation and for organizing this. I should say that I do not appreciate that you said he got his PhD back in 2007, but other than that, the rest of the introduction was very kind. But I do thank the rest of you for being here. Now, today I want to talk about our work on machine learning in graphs with a large number of nodes. And in particular, I want to explain how to use graph limits to understand the limit behavior of graph filters and graph neural networks, and explain how these limits enable this notion of learning by transference, which is a phrase that we use to describe the idea of using graph neural networks that we train in small graphs on graphs with a larger number of nodes. Now, in order to motivate the talk, which I know for a lot of you is not necessary, but maybe it is for some others, I have to begin with two preliminary questions, which are why and how. The why question is, why do we want to do machine learning on graphs? And in particular, why do we want to do machine learning on large scale graphs? And the answer to that is because there are several processes or systems that appear in the real world that necessitate this type of processing. In the slide here, I am showcasing two examples. The one on the left is trying to represent a recommendation system as those that are used on online marketing, where the idea is that different nodes of the graph represent different products. And we want to recommend products to users by predicting the rating that these different users would give to these different products. On the right, we have something that is closer to my own personal interest, which is the coordination of a swarm. So these are drones that are flying around. We want them to coordinate something, and the key characteristic of the system is the presence of a graph that limits the exchange of information. Now, so both of these, I should also say, are examples where the use of learning is well motivated, because it is very difficult for us to come up with algorithms for proposing product, actually not for proposing, for predicting product ratings. And it is also very difficult for us to come up with distributed algorithms that would allow the swarm to collaborate. So if that is difficult, learning is justified. And indeed, learning has been used in both of these problems, and it works well. But more important for this talk, both of these are also examples of systems that become more interesting as the number of nodes grows, or as the number of nodes becomes large. That is, maybe when the products that you want to rate are a couple thousand, and the drones that you want to coordinate are a couple hundred. It's not that the system is uninteresting when the number of nodes is small, but it's certainly more interesting when the number of nodes is large. Now, this also means that the problems are interesting when they are difficult, okay? Because learning in a small graph is not particularly challenging, but learning in a larger graph is quite more of a challenge. That's the why. So the how, we are in the year 2022, so we have accumulated by now more than a decade of empirical evidence that we should use neural networks. Some people can dispute that, but it's an architecture that has been shown to have a number of appealing properties. Now, the challenge with using a standard neural network, and by that I mean a fully connected neural network, is that fully connected neural networks, they do not scale. And so you cannot really utilize a fully connected neural network in a problem that has thousands of variables. The neural networks that we know scale are convolutional neural networks, and they rely on convolutions for their scalability. But the issue, of course, with convolutions is that convolutions are defined on this grid, and we want to use convolutions on this irregular graph. Okay. Now, I know that a lot of you work on graph signal processing, so you are going to tell me, well, this is not an issue at all, because in fact, we do know exactly what the solution to this problem is. And yes, this slide is showing this observation, right, of saying that scalability requires the use of a convolutional network is providing both the problem and the solution, because what we want to do to attain scalable learning on graphs is to propose a generalization of a convolutional neural network, or the convolutional neural network that applies on Euclidean space. But in order to do that, we just need to generalize convolutions from Euclidean space to graphs, and that we have done. Right? By we, I mean the community has done that. And incidentally, that is how you define graph neural networks. You get the convolutional part of a CNN layer, and you replace that by a graph convolution. Okay, now that's the how, which is, these problems with large numbers of nodes appear in reality. The how, which is use a graph neural network, which replaces convolutions in Euclidean space by convolutions on graphs. These are the two motivational answers. Now, the question, or the two questions that I would like to address in this talk are the following. Okay, we have empirically observed that GNNs scale. But the question is, why do they scale, right? So why is it that we get a GNN that operates, why is it that a GNN can solve a problem in a large scale? And related question to that, which is perhaps more interesting, is the question of, can we get the success of GNNs on moderate size graphs and conclude that that success can be translated to larger scale graphs? Okay, so the first question is, why do they scale? The second question is, can we leverage that scaling to simplify learning? In order to answer these questions, I think that it's worth to consider what happens when we look at convolutions in Euclidean space. Okay, and I should have used a painting of Degas here, but I was lazy to redo this slide that I had prepared for some other purposes. But anyway, so this is discrete time or a slash discrete image processing. Okay. Now, one reason why CNNs scale well is that images and time sequences, they have well-defined limits. Indeed, look at the sequence of images below, right? So as I scale the number of pixels here, at some point, these images stops changing. Like at the resolution of the two images on the left, they're completely indistinguishable. Okay, and that's important because it means that there is an intrinsic limit, and that intrinsic limit, there is a limit, and that limit limits the intrinsic dimensionality of the signal. Okay, so if we are given the signal on the right, which has 600 by 300 by 400 pixels, we know that this is unnecessary. We know that probably the image with 200 by 100 pixels is enough. And actually, this is leveraged when we learn with convolutional neural networks. I mean, when you look at the training of CNNs for images using CIFAR10, for example, these images are 32 by 32, so they're very low resolution images. But we train on those images because we know that there's no point on training on larger images. Okay, and that's because there's this continuous limit, and training on a low resolution image is enough to capture all of the information that the image has. Okay, so let me go back to the questions that I asked before, right? So why do they scale? Can we go from smaller graphs to larger graphs? These are the two questions. Well, I mean, in the case of images, we can, right? So we know that they scale in a sense because they have a limit, and we know that we can train on a smaller graph, a smaller image, and then transfer to a larger image. The question is, I mean, can we repeat these two arguments for graphs? In order to do that, what I need to begin by doing is by observing that graphs very often do have limits. Okay, and this is an example of this is an example of how a graph limit looks like, right? So here we have at the beginning a graph with 50 nodes, which I grow to 100, which I grow to 200, and you can see that after a while this graph sort of stops changing, and at the end of the day it has a limit. Now, and that's because if you look at the graph with 200 nodes and the graph with 100 nodes, they look essentially identical. Now, this particular case is an example of an Erdos rangy graph, which is generated from a uniform graphon. There's other ways of constructing limit there's other types of graphones that I could have depicted here, but what I want to illustrate is that there is some notion of convergence for a graph, and that limit object is what I'm going to call a graphone. Okay, and that maybe you could tell me, well, that's the end of the story, right? Because if limits in images answer the scalability questions, then limits in graphs should answer the scalability questions. Well, but not quite, right? Because the fact that there is a limit for the graph doesn't imply that there is a limit for the information processing architecture that you're running on top of this graph, okay? As I am sure you all know, right? So convergence of convolutions in Euclidean domain is something that we actually call sampling. So we don't study convergence, we study, we study it in the opposite direction. But in any event, I mean, all of our sampling results depend on geometry, and they won't translate verbatim to graphs, okay? So then the question of whether graph convolutions and GNNs converge to limit objects is one that has to be established, and that's the main purpose of this line of research that we conduct here at Penn. Now, the two results that I want to prove today are these two. I will first try to establish that graph convolutions and GNNs do converge to Graphone convolutions and Graphone neural networks. And this convergence result, I will argue, is one possible answer to one of the two fundamental questions that I posed at the beginning of the talk, which is that the empirical results showing that GNNs scale are explained by the fact that graph convolutions and GNNs have well-defined limits on the graph. Now, this is, however, an asymptotic convergence result, and we have also developed a final sample versions of this convergence result. And the purpose of this finite sample convergence result is to show that the difference between the outputs of the GNNs with the same set of parameters on a moderately sized graph and a larger sized graph is small. That is that, it's not only that you have convergence, but we also characterize explicitly, we provide an explicit bound between running a GNN on a graph with m nodes and a graph with m much larger than n nodes. Now, in terms, I think that this second result is actually the more interesting because this implies that the GNNs are transferable across this graph, meaning you can train on n nodes and then you can execute on m. And that's the title of this talk. That's why we call this learning by transference. Now, I should also add that this convergence or transferability analysis provides some interesting insights, which I will discuss in due time. But you know, I couldn't find a way of giving you a preview of how these insights look like. But you know, for the time being, we should say that we're going to establish a convergence results and a transferability analysis. Now, just because I think it's important to give you a reason to care, let me show you that these ideas are not a figment of my imagination. So here I am showing that indeed transferability is actually very useful and applicable in practice. So I have we have personally tested that in recommendation systems, and we have also tested this in collaborative intelligence systems. In the recommendation example here, I consider the training on a graph with a certain number of nodes, and then the execution on a graph with a larger number of nodes. And this plot here illustrates the performance penalty that you pay for not training on the appropriate graph. And you can see that you know, even training with something like with 600 nodes is enough to transfer all the way up to 4,000 nodes. And actually, if you look at the graph here, there's no reason to train beyond 1,000 nodes. So once you train the GNN with 1,000 products, you can transfer to 4,000 with almost no loss of performance. And in the Multirobot Consensus, the same happens. So here we are training the swarm to coordinate their velocities while avoiding collisions, as in the case of movie recommendations. You can see that the transference penalty is very small, right? So you can train with 30 nodes, execute with 100 nodes, and the performance will be just as good. And this is actually very important in practice because training here means simulating the trajectory of the system. So it is very costly to train the system. So the ability of, or the possibility of reducing the number of nodes on which you train is quite significant. Now, the other point that I want to emphasize is that if you look at both of these situations, actually it's more apparent in the case of the swarm, the GNN is transferring better than the graph filter. So you see, this is the performance penalty that the GNN pays. This is the performance penalty that the graph filter pays. So it seems that the GNN somehow transfers better. And I think that the transferability results that I'm going to provide later on will give you some indication of why this can be the case. Okay, so that's the introduction to the talk. I am now going to move into the technical part of the presentation. There's a question. Oh, no, there's not a question in the chat. It's just a gear saying that you can post questions in the chat. So nothing for me to answer at this point. So let me move to the technical part of the presentation. Now, let's begin by talking about graph convolutions. Okay, and I believe that this will be review for the vast majority of you, but you know, please bear with me. Now, graph convolutions, I think they're easiest to understand if we reinterpret convolutions in time and space as convolutions on graphs. Right? So we have been doing this for a decade by now, so this is a standard explanation. You know, like if you want to describe convolutions, you know what you do, right? So you get your own signal, you combine that signals with the signals of your one-hop neighbors, with your two-hop neighbors, with your three-hop neighbors, and so on. So that's how we construct convolutions. Right? So you get your own signal, you multiply by a coefficient, the signals of your neighbors, you multiply by another coefficient, and so on. These are neighbors in time. Now you want to do, if you want to do convolutions in images, you do the same. I mean, you begin with your own signal, then you get the signals of your neighbors, you multiply that by another coefficient, two-hop neighbors, yet another coefficient, and so on. This is describing asymmetric convolutions on images. Asymmetric convolutions are a little more challenging to describe. But in any event, right, in both of these cases, I am constructing convolutions as polynomials on the respective adjacency of a corresponding graph. In the case of time signals, I am constructing convolutions as a polynomial on the adjacency matrix of the line graph. In the case of Euclidean of 2D convolutions, I am constructing the convolutions as polynomials on the adjacency matrix of this grid graph. If I want to define now graph convolutions, what changes is that nothing changes. I keep the same definition, I just change the graph. Okay, and I begin by my own signal, which I multiply by a certain coefficient. Then I get the signals of my neighbors, which I multiply by another coefficient, the signals of my two hop neighbors, which are multiplied by another coefficient, and so on. Okay. There are other reasons for us to justify the use of the name convolution here. You can ask me later on about that. But if nothing else, you can see that these two definitions are algebraically identical. So in the case of time and graph convolutions, we define them as polynomials on the adjacency matrix of some graphs. In the case of graph convolutions, we still define the convolution as a polynomial on the adjacency matrix of a certain graph. And that's it. I mean, there's no more mystery than that to the definition of a graph convolution. Incidentally, if you are coming from the more, there's kind of like a two rivers that feed into the definitions of GNN. So one that comes more from the neural network literature, and another one that comes more from the graph signal processing literature. So if you are coming more from this, from the neural network literature, this definition of convolutions may look strange, but it is equivalent. Okay. Okay. Now we are here, however, not gathered to talk about graphs. We are here gathered to talk about graphones. In order to talk about graphones, I need to define what graphones are, okay? And graphones are actually not very complicated. They're surprisingly simple. A graphone is just a bounded, symmetric, measurable function in the 0-1 square interval, okay? Now, this definition of a graphone is constructed such that we can think of the coordinate as a label, and the corresponding value of the graphone W of UV as the weight of a graph. Now, we can give two interpretations to this graphone. The first one is that the graphone is the limit of a sequence of graphs where motifs converge, or perhaps easier to understand as a generative model of graph graph families, in which we sample labels UI, and we then connect nodes UI and UJ with probability W of IJ. That's why the restriction to have the weights between 0 and 1. But anyway, so there's three different interpretations here, right? So the graphone itself can be thought of as a weighted graph. It's just that it's a weighted graph with a dense label set instead of having like a discrete label set. The graphone can be interpreted as a limit of a sequence of graphs of different sizes, or conversely, you can get the graphone and you can sample graphs of different numbers of nodes, and you connect nodes in that graph with the probability that corresponds to the value of the graphone. Now, this is the same slide that I showed you before, but now it's given in the context of graphones. Okay, so like this structure here on the right, the blue one, that's the graphone. It's a bounded measurable function between 0 and 1. It actually has a uniform value equals to P for all points. And we utilize that graphone to sample graphs with 50, 100, or 200 nodes, and these are Erdos range graphs. You can construct more complicated graphs. This is a stochastic block model in which connections within communities have some probability, connections outside of the community have a smaller probability. And again, you can get the graphone, and out of the graphone, you can sample graphs with different numbers of nodes. But conversely, right, you can also think of this sequence of graphs converging towards the graphone. And I am not formalizing this notion, but this notion can be formalized. Okay, I have, over the last couple minutes, being given you definitions, okay? And as I always like to say when I teach, when you are giving definitions, it can get a little boring. So let me try to summarize the definitions that I have given. I have given you the definition of graph convolutions. That's a polynomial on the adjacency matrix of a graph. And I have defined a graphone, which a graphone is, I think, the easiest way to think about it. A graph that is weighted and in which the label set is a dense set, as opposed to being a discrete set, which is how we define graphs. And yes, this graphone or graphone can be used as a generative model of graphs, or it can be used as a limit object for a sequence of graphs. But if I define graph convolutions and graphones, of course, the next thing that follows is the definition of graphone convolutions. Now, let me therefore remind you that we had defined this graph convolution as a polynomial on the adjacency matrix of the graph. So that's the notion that we need to generalize. And in order to generalize that notion, the first thing that we need to generalize is the notion of matrix multiplication, right? And of course, you guys know that when you have a dense object, the equivalent of a matrix multiplication is a linear, an integral linear operator, which is what I am defining here. So I am defining the graphone shift operator as the integral of W u v times x of u. The output of that is y of b. And x and y here are what we could call like graphone signals. These are signals that are defined on top of the graphone. Once we come up with a definition of a graphone shift operator, we can actually go and look at the work of Matthew Morency and Geert Loos on graph signal processing in the limit, and you will see a definition like this one appearing over there, in which we construct a graphone filter using compositions of the graphone shift operator. We cannot use powers now because those powers, as we did in the case of matrices, because these powers are undefined now. But we can construct a composition of k applications of the graphone shift operator, and each of the individual outcomes of this diffusion sequence is multiplied by a different coefficient. Okay, let me maybe be more specific about that. TW0, that's just the identity. So you get your own graphone signal, and you multiply it by just a scalar coefficient. You then apply the diffusion operator once, the graphone shift operator once, and you multiply that by a coefficient h1. You then multiply, it's not that you multiply, sorry, you then apply this graphone shift operator once more, and you multiply that by a second scalar coefficient. Genetically speaking, you construct the so-called diffusion sequence, in which the kth element of that diffusion sequence follows from application of the graphone shift operator to the k minus first element of that diffusion sequence. And after you have constructed elements of this diffusion sequence, each element of the diffusion sequence is multiplied by a different coefficient, which you can see is the same thing that we do for graphs, right? So we have, the first element is the signal itself. The second element follows from one application of the shift operator S. The third element of the graph convolution follows from two applications of the shift operator S, which I write as S squared over here. In the case of graphones, I cannot write powers, but I can write compositions of the graphone shift operator. And that's the definition of a graphone filter, which again, it's algebraically the same, and that's, by the way, is a very interesting thing that we're not going to cover today. But we have time convolutions, image convolutions, graph convolutions, and now graphone convolutions. And in all of the cases, the algebraic structure of the operation is identical. Okay, now I still need to come up with one other definition or one other theorem, perhaps, which is that of frequency representations of graphs and graphone filters. And the reason why I need to do that is because the theorems that I am about to present on convergence of filters and transferability of filters, they depend on these frequency representations. Now, what this frequency representation result says is actually something very simple. If we are defining our graph filters as polynomials on a certain matrix, it follows that these polynomials can be diagonalized. More to the point, suppose that you consider now a sequence of graphs, and each element of the sequence is characterized by a particular shift operator. If you define your filter signals as polynomials on the respective adjacencies, and you assume that these shift operators can be diagonalized, it follows immediately that there is a spectral representation on what we call the graph Fourier domain, in which individual entries of the input are multiplied by just a scalar coefficient. There's no mixing of components. The same thing that happens when we represent time convolutions in the frequency domain. That motivates this definition of what we call the frequency representation of a graph filter, which is a polynomial on a scalar variable lambda. There's no graph at all embedded in this definition. Now, the graph is, of course, not irrelevant, right? Because what the graph does is it determines the eigenvalues at which the frequency response is instantiated. Okay, this is actually very important. So we'll give a picture to cement the idea. If you give me a graph filter, I can construct the frequency response irrespectively of the graph. It has nothing to do with the graph. I mean, it's defined here. You see that the graph is absent from this definition. But of course, I mean, if I want to capture the effect of a graph filter on a signal on a particular graph, I need to look at the specific graph. And in particular, I need to look at the specific eigenvalues of the graph, which is what this picture is trying to illustrate. Now that's for graphs. For graphones, I had this linear operator, and you guys know, or if not, you can believe me, that these integral linear operators, they also have decompositions in terms of eigenvalues and eigenfunctions, not eigenvectors, because we are talking about bounded measurable functions over here. However, the same fundamental fact still holds, which is that if we define the equivalent of a graphone Fourier transform, then the application of a graphone filter in the graphone Fourier domain is just a pointwise operation, which motivates the definition of the frequency response of a graphone filter. And this is where the fundamental observation arises, which is that actually the definition is the same, because just as the frequency response of a graph filter is independent of the graph, the frequency response of a graphone filter is independent of the graphone. Of course, I mean, the graphone is not irrelevant, because here we have the frequency representation of the graphone filter. That frequency representation, the frequency response of the graphone filter. The frequency response of the graphone filter is independent of the graph. But if I want to understand the effect of the graphone filter on a particular graphone signal, I need to instantiate at the corresponding eigenvalues, which is what this alternative picture is trying to signify. That, okay, we are given this frequency response of the graphone filter is independent of the graphone, but for a specific graphone, it is instantiated at some specific eigenvalues. Now, if you have understood these different explanations of a graphone filter and a graph filter and their corresponding frequency representations and their corresponding frequency responses, and you have seen that the frequency responses are the same, you know how I am going to establish convergence. I'm going to say, well, if the eigenvalues of the graph converge to the eigenvalues of the graphone, and the frequency representations are the same, it follows that the graph filter converges to the graphone filter. And yes, that's how you can establish this theorem, where you do need to add a restriction, by the way, which is that h of lambda, that's the frequency response, be Lipschitz. So if the frequency response is not Lipschitz, you cannot translate the convergence of eigenvalues into convergence of the frequency response. Okay. Now that is perhaps the part of the talk that is most interesting. So maybe I should review it a little bit. Okay. So first off, I reminded you of what a graph filter is. It's just a polynomial on consecutive applications of the shift operator. So I'm kind of changing the language a little bit. Okay, so I apply the shift operator 0 times. I multiply that by h0. I apply the shift operator once. I multiply that by h1. I apply the shift operator twice. I multiply that by h2. Shift operator 3 times. Multiply that by h3. That interpretation is useful in the case of graphones, because if we define this graphone shift operator as this linear integral operator, it follows that we can yet again utilize the same definition for graphone convolutions, which is that we compose different applications of the graphone shift operator. We construct this graphone diffusion sequence recursively, and each element of the graphone diffusion sequence is multiplied by a different number. Now, the really interesting fact is that both of these, and maybe you can just obviate the details of the theorems here, they're just for your reference. The very important property that this structure has, both the graph convolution and the graphone convolutions, is that both admit point-wise spectral representations. And if both admit point-wise spectral representations, they justify the definition of a frequency response, which is completely independent of the graph or the graphone, and is the same whether we consider a graph or a graphone. Now, what changes, of course, is that when we consider a graph, we are instantiating on a certain set of eigenvalues. But when we consider a graphone, we're instantiating on a different set of eigenvalues. But if the eigenvalues converge, it's not a problem, because we can translate the convergence of eigenvalues into convergence of the frequency responses, which would imply convergence of the graph filters. And that can be done, but it does require the filters to be Lipschitz. Okay, you cannot have a filter with arbitrarily fast varying changes. And of course, I mean, the convergence rate is captured by this Lipschitz constant. Now that's the theorem. I mean, it looks like the end of the story, but let me actually explain to you a little bit about convergence properties of graphone spectra. So this is how the spectrum of a graphone looks like. I mean, and it has an accumulation point at 0. Okay, as the number of nodes goes to infinity. As you let the eigenvalue index go to infinity, you get a concentration of eigenvalues around 0. Now, and what we know of convergence of graph eigenvalues to graphone eigenvalues is that yes, they do converge. But what is very interesting, or actually very important, is that the convergence of these eigenvalues is not uniform. Okay, so those eigenvalues that are closer to 0, they take longer to converge. Now, the point is that, as I already told you, right? I mean, because eigenvalues converge, we can expect graph convolutions to converge, and therefore that theorem is not surprising at all. But suppose that you wanted to construct a graph filter trying to discriminate spectral components that are close to zero. Well, that will be difficult to guarantee convergence of that filter because of two reasons, right? I mean, you can think, well, I mean, the Lipschitz constant of that filter will be very large, right? And therefore convergence holds, but it takes very large n for that convergence to manifest. But you can also see it from the pictures, I mean, right? I mean, when I am close to zero, it is very difficult for me to discriminate different eigenvalues. Now, at the end of the day, what I'm trying to explain over here is that when we look at eigenvalues close to zero, we see a trade-off between transferability, between convergence and discriminability. As we approach eigenvalues close to zero, it becomes very difficult for us to converge unless we give up the discriminability of the filter. Formally speaking, for me to have a Lipschitz filter, I am at some point unable to discriminate these eigenvalues that are concentrating around zero. Now, this cannot be captured with a convergence analysis, as I have described here, so which is the reason why we have this transferability analysis. Okay, this transferability analysis is not asymptotic; it's for finite n. And in this finite n analysis, I am going to leave you here with a theorem that involves a large number of constants. Okay, but the fundamental aspect that I want to highlight from this theorem is that, yes, we have a bound that decreases with n, but as n goes to infinity, we do have a bandwidth C here, which we cannot transfer, okay? In order for me to come up with a finite n analysis, this is what I do. I define a certain bandwidth, which is a value close to zero. And I am saying, well, you know, the eigenvalues that are outside C, I can control and I can let them go to zero. But the eigenvalues that are inside C, I cannot. Of course, I mean, as you increase n, you can reduce C, but you see, that's why we call this a trade-off, right? I mean, there is a trade-off on how thin your filters are, which means how discriminative they are close to zero, and how long it takes for you to observe convergence. Okay. Now the transferability paradigm, I told you with this, okay? So we want to begin with m nodes, and then we want to execute in a graph with m nodes. And this is not what I'm showing here because it's just conversions, but of course you can just apply the triangle inequality and you come up with a finite n and finite m bound. And what is critical about that bound is the appearance of the Lipschitz constant of the filter and the appearance of this bandwidth constancy, okay? And the reason why these bounds are relevant is because they tell you something about the filters that are transferable. If you're looking at filters that are trying to separate large eigenvalues, those filters are transferable, it's no big deal. By which I mean transferability and discriminability are compatible. I can isolate individual eigenvalues and I can transfer the filters well. However, as you start decreasing the frequency, you start seeing that in order to discriminate better, you start to need thinner and thinner filters. And that goes to the detriment of convergence. So when you consider low frequencies, transferability and discriminability, they become incompatible. Now this brings me to the introduction of graph neural networks, because I I brought you here under false pretenses. I told you that I was going to talk about graph neural networks, but I spent the whole hour talking about graph filters. But the reason for that is because graph neural networks or graphone neural networks, they're not that different from graph filters and graphone filters. In reality, this was my definition of a graph convolution. This was my definition of a graphone convolution. If I want to leverage that to construct graph neural networks, I need to stack layers, each of which is made up of a graph filter followed by application of a pointwise nonlinearity. Graph filter, pointwise nonlinearity, graph filter, pointwise nonlinearity, several layers of that. The output is a GNN. A graphone neural network is going to be the same. I mean, I concatenate a graphone filter with a pointwise nonlinearity, another graphone filter with another pointwise nonlinearity, and so on. But guys, there's a pointwise nonlinearity, right? I mean, what is the pointwise nonlinearity changing? The answer to that is a lot or nothing. I mean, from a practical perspective, that nonlinearity is the difference between day and night. Now, from an analytical perspective, pointwise nonlinearity, there's nothing there to analyze. I mean, if you know what's going on with the convolution, you know what's going on with the graph neural network. I mean, for those of you that do signal processing, I think this is a very important message, by the way, right? I mean, if you want to understand a neural network, what you need to understand actually is the convolution. So there's a big opportunity for us because we are the community that, at the very least, we are the community that teaches convolutions, right? So, if I need to explain a neural network to someone, that's how I explain it. I mean, well, let me explain convolutions to you. After I explain convolutions, I can tell you what a neural network is. It has nothing to do with mimicking the structure of the brain. It just has to do with making convolutions more applicable through the use of pointwise nonlinearity. It's a different perspective, but one that I like quite a lot. In any event, that was a parenthesis, a digression, if you wish. I define graph and graphone convolutions. If I want to construct GNNs, I combine, or graphone neural networks, I combine my graph filter with pointwise nonlinearities or my graphone filter with pointwise nonlinearities. I stack those in layers. But if I have shown convergence of graph filters to graphone filters, the convergence of GNNs to graphone neural networks follows immediately. And if you look at this theorem, it's the same theorem that I showed you before. Okay, now, but here is a very interesting observation, which is the one I want to make to close my talk, is that the difference between a graph filter and a GNN is that the nonlinearity is going to scatter energy across the whole spectrum, which is what allows for a better transferability versus discriminability trade-off. If you look at a graph filter, you need to go and identify spectral features wherever they happen to be. And if you're interested in spectral features associated with large eigenvalues, that you can solve. If you are interested, however, on spectral features associated with small eigenvalues, those spectral features, you cannot identify them with a graph filter that is stable. But when you apply that pointwise nonlinearity, this small eigenvalue is going to be scattered over other parts of the spectrum. So I cannot tell you formally that a GNN is going to be more transferable because I am making this slightly hand-wavy argument. What I can tell you is the following. A GNN and a graph filter are equally stable. And they both have the same trade-off, which is that the graph filters or the graph filters that make the GNN, they cannot be discriminative at frequencies close to zero. Okay, let me repeat that. So the GNN is made up of graph filters. Those graph filters, they cannot be discriminative for spectral features that are close to zero. However, the use of nonlinearities and the stacking of layers allows me to perform a demodulation trick, where I get these features that are associated with small eigenvalues, and I move them toward larger parts of the spectrum, where hopefully I can discriminate them with a stable filter in a subsequent layer. Now, and that I think is a property that helps explain that why this happens, which is that indeed, I mean, when you train them in practice, you see that the GNN transfers better than the graph filter, and as I already explained to you, that happens both in the case of recommendation systems and also in the case of swarms. Which brings me to the end of the talk, where these are the two messages that I wanted to give, which are that empirically, GNNs are more transferable than convolutional filters. This is true. And I think that theoretically, this is an explanation for that. I mean, GNNs are more transferable because of their mixing ability or their mixing properties in the spectral domain. And both of these messages justify this notion or this concept of learning by transference, which is that you train your GNN on a smaller size graph, but then you can execute it on a larger scale graph. That is all I have to say. So thanks a lot for listening. And I think we have some minutes for questions.
Thank you, Alejandro, for this nice presentation, connecting graph neural networks to these graphone neural networks. Very nice. So I see there's one question on the chat related to this graphone convolution. Yeah, so the question is whether that's also shift invariant like the graph convolution. Yeah. I guess it should be.
Yes. Right. If you look at the definition of the graphone convolution, where is it? You don't even need to go to the graphone convolution, right? So you can look at the graphone shift operator. The graphone shift operator is shift invariant. If you shift before applying the graphone shift operator or you shift after applying the graphone shift operator, is the same. And from that, it follows that the convolution is graphone shift invariant.
Yeah.
That's not the most important property they have, however. The more important property they have is label invariance. So if I get the graphone and I make a permutation of the real line, it's still the same graphone, and the graphone filter will be invariant to that change of labels.
Okay. Hamid, you also have a question? You can unmute yourself. Yeah.
Yes, good morning. Thank you. Thank you, Alejandro, for a very nice talk. I just wanted to ask you, if I wanted to take a step back and wanted to associate some physical and physics, I guess, to the notion of this graphone that you're defining, could I equate it with the abstract notion of least upper redundancy of a graph?
Ooh, okay, I don't know what's the least upper redundancy.
Well, because I mean, ultimately, you can take a complete graph. That's good. That also contains all the information that your your initial graph would have contained, plus whatever redundant information you added. I'm just I wanted to sort of interpret it more in the functional analytic framework, whereby you have a basis, you can have a frame, you can have an overcomplete, but you can also have the sort of the least overcomplete, if you will, right?
So I don't really know the structure or the object that you are describing, so I'm not going to give you a very good answer. But something that is maybe important to clarify is that in the graphone, you are trying to model graphs with growing numbers of nodes. So you're trying to relate a graph with 100 nodes with another graph which has 1,000 nodes, and you want to be able to say that these two graphs are similar. And they are similar because they are being sampled from the same graphone. But I don't know whether that has anything to do with your question.
Similar in the sense where they reflect the same underlying information, correct?
Oh, very good, very good. So the question is similar in what sense? That's a very good question. Okay, so the sense in which they are similar is that if you look at the motifs that appear in one graph and the motifs that appear in the other graph, all motifs have the same density or the same probability of occurring. Make sense?
Yeah. So the information is similar, then, right?
Yeah, the structure. Yeah, very good, very good. I get your question. Yes, the convergence of graphs to graphones is based on a structural similarity. And a structural similarity is defined in terms of motifs. If you count the number of triangles in one graph, normalized to the number of nodes, and then you count the number of triangles in the other graph, normalized to the number of nodes, these two quantities are convergent. But if you look at the number of cycles with 5 nodes, this is also convergent.
Okay. All right. Thank you.
Yeah. Thank you, Hamid.
Any other questions from the audience? So feel free to unmute if you want to ask a question. In the meantime, maybe I can ask a question, Alejandro. So you say that, okay, I can design a graph filter, so based on a small graph and then transfer it to larger graphs. Can you also do the opposite and design, let's say, the neural network, the graph neural network based on the graphon, and then it holds for all the sampled versions of that graphon? Because designing it for a graphon is sometimes also maybe easier than, I mean, as easy as for a small graph. Or
right. Yeah. So Gia's question is the following. I am. Let me see if I can find a picture here. I am looking at transference in this direction. Right? I'm going to say, well, let's train on this graph and execute on this other graph. And Geert is telling me, why don't we go in the opposite direction? We train here and then we execute on lower graphs. And yeah, I think that's a valuable idea. If in particular you don't want to talk about training, you want to talk about designing, because graphones tend to be easier structures than the graphs that are sampled from the graphone. So if instead of transferring learned GNNs or learned filters, you wanted to design filters, I would argue that yes, undeniably, you should design on the graphone and then transfer to the graph. And I believe that you have suggested that in your papers, and I think it's an excellent idea. In terms of training,
but here the problem is that you only have like 2, right? So you would have only 2 eigenvalues, I guess, right? 0 and the probability p. So there's not much to design, and then what do you do in between? Because
yeah.
Right. So
yes, no, that's a very good point. I mean, but but what you're highlighting is that in this particular example, this graphone is a pretty useless graphone, right? Because it's so simple. There's no real graph in reality that can be modeled with an Erdős-Rényi graphone. But the other issue that you suggested, which is maybe there's a way of training on graphones, right? I don't think that this is a bad idea either. I wouldn't know how to do it, but I think that there could be cases in which this is useful. There's in particular a lot of literature on what are called graphone games, which are limits of graph games. And in that case, you could think of solving problems on graphone games and then transferring those solutions towards graph games. But I've thought of that, but I haven't really been able to come up with a concrete idea on how to do it.
Okay, thanks. Any other questions? I see there's one more in the chat. Maybe you can also have a look. Okay. When we have a complex graph and we want to reduce the number of nodes before training, which sampling strategy would ensure that the underlying graphon remains the same? Is it as easy as random uniform sampling?
Yeah, this is a very good question. The question is about if you already start with a large graph and you want to sample that graph so that training is easier. Okay, let me begin by clarifying the two problems that I showcased, because in those two problems, I don't have sampling. In this case, if you give me 100 products, I can construct the graph for 100 products. I train on that, then I construct the graph for 1,000 products. I don't train on that. I just execute the same GNN that I learned for 100 graphs. But there's no sampling involved. It's not that I began with 100 products and then I reduce. Sorry, it's not that I began with 1,000 and then I brought it down to 100. It's that the graphs themselves are different. Of course, I mean, you can think of this as well. I mean, you know, the 100 is a sampling of the 1,000. That is true, but we didn't come up with any strategy for sampling in the 1,000 graph. Now let us go to the second one. This one, you know, we have a swarm with 50 agents. We train on that, then we generate a swarm with 100 agents. We execute on that, so there's no sampling again. Now, in some situations, maybe you are given a large graph and you want to sample that large graph so that you have a smaller dimensional object for you to train on that. And I think that's a brilliant idea. The fact that I should tell you is that this theory that I developed here is not going to tell you anything about that, because you could get your graph, use that to construct what is called an induced graphon, then you sample the induced graphon, and then this theory would be applicable. But the problem that you're trying to solve is slightly different. So I think that this theory will tell you something maybe, but not really what you want. But I can tell you actually what you want, because remember that the graph filters are spectral operators. So what you want with your sampling strategy is to respect the spectral properties of the original graph. Okay. If you do that, you will be able to transfer back and forth between the two.
Okay, Gonzalo?
Yeah, hi, thanks for the talk. Just follow up on that. Wouldn't be maybe a reasonable path? I was also thinking exactly the same question. Like, I don't know, Facebook has this huge billion node graph and then they want to train on a smaller one. Let's say, how do you kind of sample back to get representative graphs? And then could be a feasible approach. I don't know the literature exactly, but then couldn't you maybe try to do first from the large graph, do a graphon inference, kind of try to learn what a good graphon would be, and then sample from that in a way as well, like as a preserve. Again, I'm not sure how effective these graphon inference algorithms are. I know it's a hard problem just because of ordering and stuff, but then could that be a path as well? Maybe.
Yeah, so that could be a path. And that's the path that would be covered by the theory that I presented today, but I don't think is the best path to solve that problem. I think that the better path is to think about sampling strategies that respect the spectral properties of the original large-scale graph.
Thank you. Yeah.
Any other questions? Yeah, I was also wondering, so can you, so these are polynomials on the graph shift. Can you extend this also to rational polynomials, like an IIR type filters? Or can you also extend that for graphones?
I haven't done that, but I suppose that this is possible. The entire analysis here does away with the polynomial right away. We just go into the spectral domain and we operate on that spectral domain. So if you have a rational filter, the frequency response is going to be different. but the same analysis will carry through. What you would need to guarantee is that this rational filter has a Lipschitz response.
Yes, yes. Yeah. And you lose, of course, the distributed nature of the implementation potentially. Yeah.
You would lose the distributed nature of the implementation depending on that, which is not necessarily an issue.
Yeah. Okay, Danilo, you have a question?
Hi, I don't know if this is working. Hi, everyone. Thank you for the really nice talk. I was wondering, because the graph shift operator by itself, it's a bit of a mystery, because there's no universal graph shift operator, and it's not guaranteed which one is best and so on. So maybe if you can comment a little bit on that, and how does that affect the Graphone networks?
Yeah, that's another very good question. So I've been using the word adjacency quite a lot in this talk, and that's on purpose, because when you look at this Graphone shift operator is equivalent to multiplication by an adjacency matrix.
Mm-hmm.
Or not equivalent, sorry, it's the analogous of multiplication by an adjacency matrix. And you are right. I mean, there's other ways of choosing shift operators, and in each particular application, the right shift operator changes. So I haven't really done investigation of how this would extend to different types of shift operators, but again, I can just refer you back to the methodology. And the methodology is that the graph and the graphone, they are equivalent algebraic objects, which is the reason why we can define the same frequency response and conclude that the difference between the two filters is the place in which the response is sampled. So, and from that, we realize that for us to understand the convergence of the filters, it suffices for us to understand the convergence of the eigenvalues. Now, if instead of working with this definition of the shift operator, which is analogous to an adjacency, you wanted to come up with something like a normalized adjacency, or a Laplacian, or a normalized Laplacian, or a random walk Laplacian, the procedure to understand what's going on would be to understand how eigenvalues of these different entities converge to one another. And in particular, I can tell you something a little more, which is that these things, they are always going to be bounded operators. And if they are bounded operators, their spectra will always have accumulation points. And those accumulation points are the ones that are going to tell you which are the features that are difficult to transfer. Make sense?
Thank you very much.
Okay, I don't see any more questions, so I think we can then wrap up here. So thanks again, Alejandro, for giving a talk here in this webinar series. Thank you all for attending, and then we'll see you back in 2 weeks for another talk in